Hello student, welcome back to my biopsychology class. My name is Adwika and in this video we'll be talking about audition. So what we have in this video, first of all, we will review about the sound in the ear and then continue to pitch perception, and we'll be talking about the auditory cortex and about hearing loss and finally about sound localization. Let's take a look at our first topic, the sound in the ear. So basically, we hearing something is in order to extract useful information, right? So for example, if you hear footstep in your home while you're home alone, that you might recognize that someone might be near you, right? So it means that we hear something is in order to extract useful information for us. So let's check several terms related to physics and psychology of sound first, okay? So as you might know, sound waves are periodic compression of air, water, or other media. So for example, when a tree falls, the tree and the ground vibrate, right? And then setting up sound waves in the air that strike our ears. And the sound waves actually vary in amplitude and frequency. So the amplitude of sound wave is its intensity. It means that sounds of greater amplitude seems louder. And then the frequency of a sound is number of compression per second, and it measured in hertz, or the cycles per sound. The cycle per second. And then there's also terms called pitch. It related to the aspect of perception. Yeah, and sounds that higher in frequency are actually higher in pitch as well. So as you can see in this figure, it illustrates the amplitude and the frequency of sound. So the height of each wave corresponds to the amplitude, and the number of waves per second corresponds to the frequency. So most adult humans hear sound starting at about 15 to 20 hertz and ranging up to almost 20,000 hertz. And in addition to amplitude and pitch, the third aspect of sound is timbre, meaning the tone quality or tone complexity. So for example, two musical instruments playing at the same note at the same loudness might sound different. So as do two people singing the same note at the same loudness, yeah, they might also sound different. So the amount of each harmonic differs among instruments as well as among people singing. So people communicate emotion by alteration in pitch, loudness, and timbre. For example, the way you say, "That was interesting," this could indicate approval, right? Or, that was interesting. It will indicate that it was boring. It's kind of sarcasm. Or, that was interesting. It might indicate suspicion. You think someone was hinting something, right? So, so it means that prosody, it called as prosody, is conveying emotional information by tone of voice. And let's take a look at the structure of the ear first. So the anatomist distinguish the outer ear, the middle ear, and the inner ear, as you can see in this figure. And the outer ear here includes the pinna, yeah, or the familiar structure of flesh and cartilage attached to each side of our head, yeah. And by altering the reflection of sound wave, the pinna help us locate the source of a sound. So we have to learn to use that information because each person pinna is shaped differently from anyone else's. And it will affect how help us locate the sound, the source of a sound. And after sound waves pass through the auditory canal, they enter the middle ear. And when sound waves reach the middle ear, they vibrate the tympanic membrane or the eardrum, yeah. And the tympanic membrane here connects to the three tiny bones that transmit the vibration to the oval window. It's a membrane of the inner ear. And these bones, the smallest bones in the body actually, are sometimes known by the English names called the hammer, anvil, and stirrup, and sometimes also by Latin names called malleus, incus, and stapes. But those are the same organ actually. And then the tympanic membrane is about 20 times larger than a footplate of the stirrup, which connect to the oval window. Yeah, as in a hydraulic pump, the vibration of the tympanic membranes is actually amplified into more forceful vibration of the smaller stirrup, right? And the net effect of it is converts the sound wave into waves of greater pressure on the small oval window. And then continue into the inner ear. Sorry, it's mistakenly written. It should be inner ear. Yeah. So when the stirrups vibrate the oval window, it sets into motion the fluid in the cochlea. Yeah. It's the snail-shaped structure in the inner ear, as you can see in this figure as well. It shows a cross-section through the cochlea and its tunnel. And then the auditory receptors known as hair cells, it lie between the basilar membrane of the cochlea on one side and the tectorial membrane on the other side. And then the vibration in the fluid of the cochlea displays the hair cells here and thereby opening ion channels in its membrane. And as you can see in this figure, it shows an electron micrograph of human hair cells here, and the hair cells stimulate the cells of the auditory nerve, which is part of the 8th cranial nerve. All right, so we're moving on to the pitch perception. What is pitch perception? So it is actually your ability to understand speech or enjoy music depends on your ability to differentiate among sounds or different frequency. But the question is, how do you do it? So to explain pitch perception, there are 3 theories. The first one is the place theory. According to this theory, the basilar membrane resembles the string of a piano, which each area along the membrane tune to a specific frequency. So if you sound a note with a tuning fork near a piano, you vibrate the piano strings, turn to that note, right? And according to this theory, each frequency will activate the hair cells at only one place along the basilar membrane, and the nervous system distinguishes among frequencies based on which neurons respond. And the downfall of this theory is that the various parts of the basilar membrane are bound together too tightly for any part to resonate like a piano string. So there is another theory, which is the frequency theory. So it indicates that the entire basilar membrane vibrates in synchrony with the sound, causing auditory nerve axon to produce action potential at the same frequency. So for example, a sound at 50 Hertz would cause 50 action potential per second in the auditory nerve. So, but the downfall of this theory in its simplest form is that the refractory period of a neuron, though variable among neurons, is typically about 1 per 1,000 seconds. So the maximum firing rate of a neuron is about 1,000 Hertz. It's far short of the highest frequencies we hear. And the current theory that is used is a modification of both theory, the place and the frequency. So for low frequency sound, or up to about 100 Hertz, more than an octave below middle C in the music, which is 264 Hertz, yeah. So the basilar membrane vibrates in synchrony with the sound wave. It's in accordance with the frequency theory, and the auditory nerve axon generate 1 action potential per wave. So soft sounds activate fewer neurons, and stronger sounds activate more. Those at low frequency, the frequency of impulses identify the pitch, and the number of firing cells identify loudness. But then as sound exceeds 100 hertz, it becomes harder for any neurons to continue firing in synchrony with the sound waves. At higher frequencies, a neuron might fire on some of the waves and not others. Its action potential are phase locked to the peaks of the sound wave. As you can see it illustrated in this figure, each wave a high frequency tone excite at least a 3. But then how do we perceive high frequency sounds that is above 400 hertz with few auditory neurons? So according to the Foley principle of pitch discrimination, the auditory nerve as a whole produces volleys of impulses for sound up to about 4,000 per second, even though no individual axon approaches that frequency. However, beyond about 4,000 hertz, even staggered volleys of impulses cannot keep pace with the sound waves. And as you might know that most human hearing take places below 4,000 hertz, the approximate limit of the Foley principle. So for comparison, the highest key on a piano is for 1,224 hertz. When we hear still higher frequency, we use a mechanic similar to the place theory. And the basilar membrane varies from stiff at its base, where the stirrup meets the cochlea, to floppy at the other end of the cochlea, the apex, as you can see in this figure. And a high-pitched sound set up a traveling wave that peaks at some point along the basilar membrane and then stops. The point at which it peaks identifies the frequency of the sound, and the highest frequency sounds vibrate higher hair cells near the base, and lower frequency sounds vibrate hair cells farther along the membrane. All right, let's moving on to the auditory cortex. As information from the auditory system passes through subcortical areas, axons cross over in the midbrain to enable each hemisphere of the forebrain to get most of its input from the opposite ear. So the information ultimately reaches the primary auditory cortex, as you can see in this figure, or the area of A1 in the superior temporal cortex. And the organization of the auditory cortex is parallels that of the visual cortex. For example, just as the visual system has separate pathways for identifying objects and acting upon them, the auditory system also has a pathway in the anterior temporal cortex, which specializes for identifying sound, and a pathway in the posterior temporal cortex and the parietal cortex specialized for locating the sounds. All right, just as patients with damage in area of MT, they become motion blind, and this also happened with patients with damage in part of their superior temporal cortex, they become motion deaf. What does it mean? So it means that they hear sounds, but they do not detect that a source of a sound is actually moving. So just as the visual cortex is active during visual imagery, area A1 or the superior temporal cortex responds to imagined sound as well as real ones. It's very interesting. It becomes active when people view short silent video that suggests sounds, such as someone playing a piano or a glass vase shattering on the ground. Yeah. In one study, people listened to several familiar and unfamiliar songs, and at various points, part of each song were replaced by 3 to 5 second gaps, yeah, with silence. And then people were listening to a familiar songs, and they reported that they heard in their heads, yeah, the notes or word that belong in the gaps. So that experience was accompanied by activity in area A1, actually. So during similar gaps in the unfamiliar song, they did not hear anything in their heads, and area A1 also showed no response at all. Also, like the visual system, the development of the auditory system depends on experience. Just as rearing an animal in the dark impairs visual development, Rearing one in constant noise impairs the auditory development. All right. However, the visual and auditory system differ in this respect. So whereas damage to the primary visual cortex leaves someone behind, someone blind, damage to the primary auditory cortex does not produce deafness. So people with damage to the primary auditory cortex have trouble with speech and music, but they still can identify and localize single sound. Evidently, the cortex is not necessary for hearing, but it is necessary for processing the information. So when researchers record from cells in the primary auditory cortex when they're playing pure tones, they found that most cells have a preferred tone. So the auditory cortex actually provides what researchers call as a tone-topic map of sound, as you may see in this figure. So note that the cells responsive to similar frequency tend to group together. So the tonotomic map differs in detail from one person to another. The auditory cortex is also important not just for hearing, but also important for thinking about the concept related to hearing. For example, people were asked to look at letter arrays and press a button to indicate whether each one was or was not a real word. So the test was easy enough that most people were almost always correct, actually, but people with damage to the auditory cortex performed normally except for words relating to sounds. Yeah. Not always, but frequently they might look at something like thunder, indicate no, that is not a word. So according to that study, it's significant actually, as it supports that the theory that human concepts rely on association with the sensation or action that initially established them. So if you cannot imagine a sound, then a word relating to sound is actually seem meaningless. And the next topic is about sound localization. So you imagine this, that you were walking alone when suddenly you hear a loud noise. So you want to know what produced it, yeah. But but equally, you want to know where it came from as well, right? So sound localization is less accurate than visual localization, but nevertheless, it's impressive actually. So for example, owls localize sounds well enough to capture mice in the dark. And determining the direction and distance of a sound, it requires comparing the responses of two ears, right? So one method is the difference in time of arrival at the two ears. So a sound coming directly from one side reaches your closer ear about 600 microseconds before the other. And a smaller difference in arrival times indicate a sound source nearer to your midline, actually. So time of arrival is useful for localizing sound with a sudden onset. So for example, most birds' alarm calls increase gradually in loudness and making them difficult for a predator to localize. And another cue for localization is the difference in intensity between ears. So for a high frequency sound with a wavelength shorter than the width of the head then creates a sound shadow, as you can see in this figure. So making the sound louder for the it makes the sound louder for the closer ear, actually. In adult humans, this mechanism produces accurate sound localization for frequencies above 2000 to 3000 Hertz and less accurate localization for the lower frequency. And the last cue is the phase difference between the ears. So every sound wave has phase with peaks 360 degrees apart. And in this figure, it shows sound waves that are in phase or out of phase. If a sound originates to the side of the head, the sound waves strike two ears out of pace as shown in this figure. So how much of pace depends on the frequency of the sound is the size of the head and the direction of the sound. And pace differences provide information that is useful for localizing sound, which frequency up to 1,500 hertz in humans. And speed sounds and music are well within in this range. All right, so we will talking about amusia. So an estimate of 4% of people have amusia. It is a commonly called as tone deafness, what it is. Um, uh, so although not really unable to detect differences in tones, they generally do not detect a change less than about the difference between C or C sharp. And furthermore, they have trouble in recognizing tunes. They cannot tell whether someone is singing off key or do not detect a wrong note in a melody. They also have trouble gauging people's mood, such as happy or sad, from the tone of their voices. For people with amusia, the auditory cortex appears to be approximately normal, but it has fewer than average connection to the frontal cortex. That is, the deficit is evidently not in hearing itself, but rather these people have poor memory for pitch and perhaps poor attention to pitch. And the implication is that amusia results from either an impairment of the prefrontal cortex or input to it from the auditory cortex. And the absolute pitch or the perfect pitch, yeah, is the ability to hear a note and identify it perfectly. For example, people can recognize a note B flat by only hearing it. And genetic predisposition is contributes to pitch perfect here, but early musical training is also important to have a pitch perfect. And not everyone with musical training develops absolute pitch, but almost everyone with absolute pitch had early musical training. And absolute pitch is also are more common among people who speak tonal languages as Vietnamese and Mandarin Chinese. So in those languages, the meaning of a sound depends on its pitch, and therefore people learn from infancy to pay close attention to slight changes of the pitch. All right, so although few people are totally unable to hear, many people have enough impairment to prevent speech comprehension here. And two categories of hearing loss are conductive deafness and the nerve deafness. The first one is the conductive deafness, is the caused by disease, infection, or tumorous bone growth, and it can prevent the middle ear from transmitting sound waves properly to the cochlea. And the result is the conductive deafness. It can persist, and it can be corrected by surgery or by hearing aids that amplify the sounds. And because people with conductive deafness sorry, have a normal cochlea and auditory nerve, they readily hear their own voice, and they conduct it through the bones of the skull directly to the cochlea, bypassing the middle ear. And because they hear themselves clearly, they may accuse others of mumbling or talking too softly. And the other one is the nerve deafness or inner ear deafness. It results from the damage to the cochlea, the hair cells, or the auditory nerve. If it is confined to one part of the cochlea, it impairs the hearing of certain frequency and not others. Nerve deafness here can be inherited. It can be resulted from disease or from exposure to loud noises. And many older people have hearing problems despite their wearing hearing aids, yeah. And the hearing aids make the sound loud enough, but elder people still have trouble understanding speech. especially in a noisy room or if someone speaks rapidly. Why this happens? So part of the explanation is that the brain areas responsible for language comprehension have become less active in elderly. This trend might be just natural deterioration, or it might be a reaction to prolonged degradation of auditory input. That is, if someone delays getting hearing aids, the language cortex doesn't get its normal input and it begins to become less responsive. And the rest of explanation relates to the attention as well. So frequently you want to listen to one person in a noisy room, and to hear what you care about, you need to filter out all the other sounds, right? And healthy young people can filter out irrelevant sounds highly effectively. But many older people have loss of inhibitory neurotransmitter in the auditory portion of the brain. And as a result, they have trouble suppressing irrelevant sounds. Also, because of decreased inhibitory transmission, the auditory cortex has gradual spread out responses to each sound instead of a quick, crisp response to each tone. So therefore, the response to one sound partly overlaps the response to another. And attention improve if the listener watch the speaker face. Yeah, it will help. We in fact, we all do more lip reading than we realize, and focusing on the speaker helps us to lock attention onto the corresponding sounds. And many older people then can attend to their voice more effectively than other voices. All right, and that's all for the topic of audition. Thank you for watching, and I'll see you soon.